Synchronous counters describe counter circuits where all of the flip-flops in the circuit share a common clock signal. The process of designing a synchronous counter starts by drawing a state diagram. To go from a state diagram to a working circuit, we use something called a transition table. A transition table is essentially a truth table for a sequential circuit. It contains all of the possible output values of each of the flip-flops in the circuit, and then has next state columns representing the next values that should be present on the flip-flop outputs once the clock ticks. Flip-flop value columns are used to determine what value should be present on a flip-flop input to generate that transition. Then, K-maps, Quine-McCluskey, or Boolean algebra can be used to derive next state expressions for each flip-flop. A typical counter will start at 0, increment by 1, and then continue to increment until reaching 2 to the n minus 1, where n is the number of flip-flops in the counter, and then reset back to 0 and continue again. Let's design a 3-bit counter that counts up. The state diagram for this counter represents each of the states of this circuit. Assuming we reset the circuit to start it in a 0 state, when the clock ticks, the flip-flop outputs will become 001, then 010, then 011, and so on. The transition table can be used to design the circuit. At this point, as the circuit designer, we must make a decision about what type of flip-flop to use. Let's design this counter using T flip-flops. Our transition table contains a column of current state values. Note that I use a modified gray code in my transition tables. This will hopefully make it easier to put data from our transition tables into our K-maps to solve for expression values. The next column contains the next state values. By looking at the state diagram, we figure out where the circuit goes next and represent that as a binary value in the transition table. If the current state is 0, then the next state is 1. If the current state is 1, the next state is 2, and so on. The last column contains the values that need to be present on each flip-flop input to cause the transition from the current state to the next state. T flip-flops have relatively simple transitions. The input value should be 0 if the output holds, and 1 when the output toggles. For example, when going from 000 to 001, flip-flop A, the most significant bit, holds, which requires an input value of 0. Flip-flop B also holds, which requires an input value of 0. And flip-flop C, the least significant bit, toggles. This requires an input value of 1. Going from 001 to 010, we need hold, toggle, toggle. The flip-flop values are 0, 1, 1. Continue until all flip-flop input values are filled out. Now that the transition table is complete, we can take the flip-flop values and put them into a K-map to solve for each input expression. The input values required for flip-flop A will go into a K-map. I will call this expression TA, the input to toggle flip-flop A. The input values are A, the current output value of flip-flop A, B, the current output value of flip-flop B, and C, the current output value of flip-flop C. When putting data into the K-map, be careful to respect gray code, which should be made simpler by the layout of our transition table. We can loop either SOP or POS and derive a minimum expression for TA, which is equal to BC. Repeating this exercise for the input to flip-flop B, we get a minimum expression of C. Noting that the value of flip-flop C is always 1, that indicates to us that the input to flip-flop C will be connected directly to VCC. How do we wire this up? This circuit is fully autonomous and requires no input values from us whatsoever, so there will be no dip switches or push buttons. The 3 flip-flops all share a common clock signal. The input to flip-flop A is the AND of the outputs of flip-flops B and C. The input to flip-flop B is the output of flip-flop C. The input to flip-flop C is VCC. After this circuit is powered up, each time the clock ticks, the counter will increment as dictated by our expressions, which should hopefully align with our state diagram. If we want to connect the outputs to a BCD to 7-segment decoder, we can watch the counter count through its sequence and confirm that it works. Let's design a 3-bit counter that counts down. Note that the state diagram now has the arrows pointing in the direction that represents counting from 7 to 0 and then back again. Let's use D flip-flops this time. The transition table again has a modified gray code for current state values. When in state 0, the next state will be 7, 1, 1, 1. When in state 1, the next state will be 0, 0, 0, 0, and so on. Typically, we'd be considering the flip-flop input values required to make these transitions. However, a D flip-flop has input values equal to the next state, so this column is not necessary when designing a counter with D flip-flops. We can take each next state column and put it into a K-map to solve for each expression. dA, the input to flip-flop A, is equal to A prime B prime C prime plus AC plus AB. If you notice the checkerboard pattern on the K-map, it points to an XOR or XNOR relationship. Let's factor out the A and get A prime B prime C prime plus A times B plus C. De Morgan's law tells us that B prime C prime is equal to the quantity of B plus C prime. So we can rewrite this as A prime times the quantity of B plus C prime plus A times the quantity of B plus C, which is A XNOR the quantity of B plus C. Because we don't have XNOR gates, we can make use of the relationship X XNOR Y is equal to X prime XOR Y to obtain the expression dA equals A prime XOR the quantity of B plus C. While we can prime either variable in the expression to go from XNOR to XOR, there's a reason we prime A and not the quantity of B plus C. This is because we get A prime for free from the flip-flop and it doesn't require an external inverter. If we primed the quantity of B plus C, we'd need an external inverter to do that. We want to make these circuits as simple to wire as possible. For dB, we see that the expression is BC plus B prime C prime, which is another XNOR relationship. Again, we want to utilize XOR instead and either get dB is equal to B prime XOR C or dB is equal to B XOR C prime, which are equivalent expressions. Finally, we can put the DC columns into a K-map and find that DC is equal to C prime. This makes sense because the counter is constantly going between even and odd numbers, so the least significant bit, C, is always going to be toggling. Wire this up by drawing out 3 flip-flops with a shared clock signal. Flip-flop A has an input of A prime XORed with the quantity B plus C. Flip-flop B has an input of B prime XORed with C. Flip-flop C has an input of C prime. We can wire this up with 3 D flip-flops and then use a BCD to 7-segment decoder on the output values to watch the counter execute the states shown in the state diagram. Now let's do something slightly different. Let's design a counter that starts at 7 and then counts down to 0 and stays there. The state diagram looks similar to the previous one, except that once we get to state 0, the arrow shows a return to the same state. Let's use a D flip-flop. The transition table has all of our current states and next states. Remember that with the D flip-flop, we don't need a separate column for flip-flop inputs because they will be equal to the next state values. After entering each next state column into a K-map, we obtain expressions of dA equals A times B plus C, dB equals BC plus A B prime C prime, and DC equals C prime times A plus B. The circuit diagram is generated the same as the other sequential circuits we've seen so far. Connect the clock input to a common clock signal, then wire up the input values. Once the flip-flops complete their countdown, the output will remain at 0 indefinitely. What if we want to watch the cycle again? We can asynchronously set each flip-flop, giving each output a value of 1. This will use the flip-flop's asynchronous preset pins. We can connect these to a momentary active low push button. We can see that once I press the button, it once again follows the state diagram. If there are no asynchronous preset and clear pins, then that flip-flop may not be a good choice for this circuit. At times, it may be useful to stop counting at a particular number. When counting from 0 to n, that counter would be known as a modulo n+1 counter. Let's design a modulo 6 counter with JK flip-flops. This counter will count from 0 to 5 repeatedly, which is a design that may be familiar in the tens place of minutes and seconds on digital clocks. The transition table has current states and next states as usual. What's the next state for current states of 6 and 7? We don't expect those states to occur in normal operation, so they can be considered to be don't cares. In reality, we should confirm with our final expressions that if the circuit were to initialize with a value of either 6 or 7, that it will enter the regular count sequence. Alternatively, we can include an active low push button connected to the asynchronous clear pin on each flip-flop to ensure that the circuit can be initialized in a 0 state. For this circuit, I confirmed the state diagram for each potential output value leads to a valid next state. So I treated states 6 and 7 as don't cares and didn't use an external push button. If the circuit initializes in state 6 or 7, this particular circuit won't run into any issues. The flip-flop values for JK flip-flops require knowledge of each transition of a JK flip-flop. These are tricky to remember, and I always refer to the equation sheet to recall what these are. They are not worth trying to memorize. Each time we have a current state of 0 and a next state of 0, the J input of the flip-flop must be 0, and the K input is a don't care. Each time we have a current state of 0 and a next state of 1, the J input will be 1, and the K input will be a don't care. When the current state is 1 and the next state is 0, the J input is a don't care, and the K input is a 1. When the current state is 1 and the next state is 1, the J input is a don't care, and the K input is 0. While JK flip-flops require twice as many expressions, the expressions are typically, but not always, easier expressions due to the abundance of don't cares. In this example, the JA input is BC, the KA input is C, the JB input is A prime C, the KB input is C. Both the J and K inputs to flip-flop C are 1, so those will connect directly to VCC. Wire up the counter and confirm that it operates as expected in accordance with the state diagram. Maybe we want a counter that can count either up or down depending on the state of an input device, such as a toggle switch. The state diagram is now going to be slightly more complicated as the arrows will include the value of the input variable that is required to make each transition. Let's say the counter counts down when the input value, x, is 0. It counts up when the input value, x, is 1. The transition table will also be more complicated because now our next states are a function of x as well as the current state. Let's design this with a toggle flip-flop. The transition table may be more complicated, but it follows the exact same procedure that we used earlier. What are the next state values when x is equal to 0? How about when x is equal to 1? Then, consider the input values required on each flip-flop to generate these transitions. The K-maps will now be 4 variable K-maps because each flip-flop expression is a function of x and the current state. When putting data from the transition table into the K-map, go one column at a time. Ask, where is x equal to 0 and a equals to 0? That goes into the 0, 0 column of the K-map. Where is x equal to 0 and a equals to 1? That goes into the 0, 1 column. Where is x equal to 1 and a equals to 0? That goes into the 1, 0 column. Finally, where x equals 1 and a equals 1 goes into the 1, 1 column. The input to toggle flip-flop A is equal to x prime b prime c prime plus xbc. For toggle flip-flop B, we get x prime c prime plus xc, or x, x, nor c. In this case, we want to use XOR. It doesn't really matter which input we prime to get XOR, because we already need to prime the input value x for flip-flop A, but generally it's best to prime a flip-flop value because that's accessible for free. So the input to flip-flop B equals x, XOR c prime. Flip-flop C has an input of 1, so that will connect directly to VCC. We can wire this up and demonstrate that it works. When I change the status of the toggle switch, the counter goes from counting up to down, or vice versa. A decade counter is a counter that counts from 0 to 9, either up or down. The state diagram depicts this. You'll build a synchronous decade counter in lab, so I won't spoil the fun about what the expressions are. The same process goes into building a decade counter, but now there are 4 flip-flops required to build this. What happens in the transition table when the current state is 10 or higher? Treat those as don't care situations. It's also possible to build a synchronous counter that uses non-consecutive values in its count sequence. I'm going to purposefully not talk about this in this video, as I really want to do an example of this in class to demonstrate some of the pitfalls of designing finite state machines. Sorry for the suspense, but it'll be worth waiting for.